I'm sharing my screen. 1 second. Is my screen is visible?
Yes, sir.
Okay. So we completed with the last class. We completed with this PN junction diode in forward bias, reverse bias, and so we seen the operation with respect to forward bias, reverse bias, with respect to electric field, and with respect to energy band diagram, with respect to width of the depletion layer. So in the forward bias, width of the depletion layer will decrease, and in the reverse bias, width of the depletion layer will increase. Okay. And next we will see about the basic ideal and practical diode. So what is this ideal diode? Ideal diode is nothing but so 1 second. Yeah. Point. Pen is not okay. So here this is ideal diode. 1 second. Yeah. So ideal diode is nothing but you have like so during so forward reverse bias it is acting as a open switch. Okay. During the forward bias it is acting as a closed switch. Okay. So during the so here yeah, during this reverse bias it is acting as a uh, open switch. See here, so diode approximations. Okay, ideal versus practical diode. Okay, so diode so when diode is turned on forward bias it is acting as short circuit, and when diode will be turned off it is acting as a open circuit. Okay, so see here, in the reverse bias it is acting as short circuit, and in forward bias it is acting as open short circuit, and reverse bias it is acting as open circuit. So if you see the characteristics, how the characteristics will be there. So in open circuit there is no current, so that means current equal to what? 0. Okay, so there is no current. And in forward bias current equal to what? Current is more current, and voltage equal to 0. Voltage equal to 0. So that means if you see, so here if you see in the so current is more in the forward bias. This is nothing but, so we are approximating, we got the characteristics. No, what characteristics you got? So like forward bias characteristics till 0.7 volts you got this, and after that there is exponential increase in the current. And in the reverse bias so there is small amount of current, and after means after uh, after going into this breakdown voltage, there is a high increase in the current. Okay, so after breakdown what happens means this acquire kinetic energy, and that will collide with each other, that electrons will collide with each other, and this will acquire kinetic energy. There is a large increase in the current. Okay, in reverse bias. So here what happens, current is so current is here more current, and voltage equal to 0. And here so in the reverse bias what happens, current equal to 0, so I equal to 0, here V equal to 0, here I equal to 0, and V equal to 0. Okay, so this is about this forward bias and reverse bias. Yeah, do you understood what is this forward bias and reverse bias? Shall I move forward? Ideal characteristics, give response.
Yes, sir.
Okay, next you see. So next second approximation. So in the second approximation what you are doing, you are adding so along with the ideal characteristics you are adding the cut-in voltage. What is that cut-in voltage? V gamma, we already seen, no? So barrier voltage or cut-in voltage for silicon, okay, is how much? 0.7 volts, and for germanium this is how much? 0.3 volts. Okay, till this depletion layer will withstand. After that depletion layer will disappear, and there is a huge increase in the current, exponential increase in the current. Okay, so we are adding, that means 0.7 volts per silicon, and here also I am adding 0.7 volts per silicon. Okay, so that means we are adding along with the diode, that is what that is a built-in voltage, built-in potential. Okay, we are adding that is series with the diode. So what happens, so that means in reverse bias it is same as ideal characteristics only. In reverse bias, whatever the ideal characteristics are there, that you got same. Okay, so but in forward bias, so in forward bias what happens, in forward bias, so this will be shifted towards what, 0.7 volts. This will be shifted towards 0.7 volts. Okay, so this is the characteristics for second approximation. So in first approximation, that is ideal characteristics, that means what, we are making as ideal diode. So ideal diode during forward bias, that is off state, on state means short circuit, and during the reverse bias, that is open circuit. And for in the second approximation, we are adding the 0.7 volts for silicon, that is cut in voltage, so that what happens here, this will be like it will be shifted towards 0.7 volts. Okay, this is second approximation. Okay, next third approximation you see. So third approximation, here along with the cut in voltage, we are adding the diode internal resistance. Okay, so along with the diode built-in potential, what is the built-in potential? V gamma. Diode built-in potential is V gamma. Along with V gamma, we are adding a diode resistance. There will be a diode internal resistance will be now. Let us take RD. RD is nothing but diode internal resistance. Okay. So due to this diode internal resistance, what happens here anyway in reverse bias, this is same as ideal only. Okay. Reverse bias, there is no change. Okay, in the reverse bias there is no change, but in the forward bias what happens, curve will be like slightly it will tilt. Why? Because due to this resistance. What is the slope of this curve? Slope of the curve is 1 by RD. Slope of the curve is 1 by RD. Okay, so this is third approximation. Okay, first approximation is nothing but what, ideal characteristics. Okay, ideal diode, ideal approximation. And second approximation is so we are adding the built-in potential, that is V gamma. And third approximation is we are adding the diode resistance. Okay, these are the three approximations. Yeah, any doubt in this approximations? Give response so that I will move forward.
No, sir.
Yeah.
Yes, sir.
Okay, next you see. So next diode rating. Diode rating means there is a maximum forward current is there. So this is the highest instantaneous current that under forward bias condition that can flow through the junction. That is nothing but maximum forward current. There is a peak inverse voltage. Peak inverse voltage is nothing but it is maximum reverse bias voltage that can be applied to PN junction. If the voltage across the junction exceeds peak inverse voltage under reverse bias, junction get damaged. Okay, how much of maximum voltage we are applying to the applied to the this diode in the reverse bias condition, that is nothing but peak inversion. After that peak inversion voltage, what happens, the diode may damage, that is nothing but peak inverse voltage. Okay, and maximum power rating, maximum power, these are some specifications for the diode. Okay, so it is the maximum power that can be dissipated at the junction without damaging the junction. Okay, how much of maximum power that is dissipating at the junction, that is nothing but maximum power rating. Okay, these are some diode ratings. Okay, so these are some diode ratings. And next we will see the effect of temperature and PN junction diode. Okay, effect of temperature in PN junction diode, if you see. So I told you, know, in forward bias condition there is effect of temperature, and reverse bias condition also there is effect of temperature. So we will discuss what is this effect of temperature during the forward bias and reverse bias condition. Okay, so one second. Pen is disabled here. Why pen is disabled? Pointer. Okay. So here if you see, yeah. So this is effect of temperature in PN junction diode characteristics. So if you see the in forward bias characteristics, the forward bias characteristics that means characteristics in forward bias has shifted towards the left side by increasing the temperature at 2.5 millivolts per degree Celsius. Okay. So that means if you increase the temperature, the curve will be shifted towards left at what temperature? Per 1 degree Celsius, the curve will be shifted towards left by how much? 2.5 millivolts per degree Celsius. Okay. So if you, that means if you are increasing the temperature, suppose if you are decreasing the temperature, the curve will be shifted towards right. Okay, the curve will be shifted towards right. So let us take, we will try to understand with this example. Find the threshold voltage at 75 degrees Celsius and minus 100 degrees Celsius for the silicon diode. If the threshold voltage is what? 25 degrees Celsius is room temperature. He given the threshold voltage, how much? 0.7. Threshold voltage or cut-in voltage, or we can call as barrier voltage. Okay, this is the given threshold voltage. Vt is the threshold voltage. So what happens here? This is the formula. What is the formula? So that means Vt 75 degrees Celsius, this is equal to, I can write as Vt naught minus delta T into this is 25 into 10 power minus 3. 25 into 10 power minus 3 is nothing but this is Vt, thermal voltage. Thermal voltage is equal to what? Kt by Q. Kt by Q, I told you, no, 26 millivolts, or we can approximate to 25 millivolts. 25 millivolts means what? 25 into 10 power minus 3 volts. Okay, so that is this formula. And delta T, so delta T equal to change in the temperature. So change in the temperature is what? T2 minus T1. So T2 minus T1 is nothing but 75 minus 25. How much you are getting? This is 50 degrees Celsius. Okay, so that is Vt naught. Vt naught equal to how much? He given, that means threshold voltage at room temperature. So what is the threshold voltage at room temperature? 0.7 volts. Okay, so that means 0.7 minus what you got? 50 delta T is 50 into 25 into 10 power minus 3. So here you are getting in 0.575 volts. Okay, so initially this is 0.7 volts. The curve, so if you increase the temperature by 75 degrees Celsius, you are getting this curve at 0.575 degrees Celsius. 0.575 degrees Celsius. Okay, so this is for what? This is for if you increase the temperature. Okay, next if you decrease the temperature, what happens? Formula is Vt naught plus, why? The curve will be shifted towards right, so plus you need to take, and delta T, so delta T equal to what? T2 minus T1. Okay, so T2 minus T1 means anyway so minus 100 minus 25. So here you are getting minus 125. Minus into minus means what? Plus you are getting. So plus 125 into 25 into 10 power minus 3. You are getting the value is how much? 1.0125. So here this is 1.0125. If you increase the temperature, the curve will be shifted towards left. Okay, and if you decrease the temperature, the curve will be shifted towards what? Right. Okay, the curve will be shifted towards right. Okay, so this is the effect of temperature in PN junction diode in forward bias condition. Forward bias condition. Okay, is it fine? Do you understood? Give response. Anyone?
Yes, sir.
Okay, so this is effect of temperature. And next, if you see under reverse bias condition, what is the effect of temperature? So in the reverse bias condition, what happens? In the reverse bias condition, there is no forward current. Okay, there is no forward current. There is a reverse current will be there. That reverse current is due to what? Reverse current is due to minority carriers. Okay, so my reverse current is due to minority carriers. So that means we already discussed. So in P side, what are the minority carriers? Electrons. In N side, what are the minority carriers? Holes are the minority carriers. So that means in reverse bias condition, the current get doubles. The current get doubles for how much? For every 10 degrees rise in temperature. For every 10 degrees rise in temperature. Suppose let us consider at 25 degrees Celsius, the reverse saturation current, let us take a is not equal to, I told you no, that reverse saturation current is very small, either it may be in terms of microamps and nanoamps, I told you. Okay, so here if you take so if you increase like 35 degrees Celsius, 35 degrees Celsius means what happens, is not becomes 100 nanoamps. Okay, it will be double. Okay, it will be double. So if it is 45 degrees Celsius, the is not becomes what, is not becomes 200 nanoamps, 200 nanoamps. Okay, like that. Okay, so we try to understand with this problem. Okay, this is the formula. What is this formula? So is equal to is naught is naught into 2 power delta t. Okay, 2 power delta t divided by 10. This is my formula, 2 power delta t divided by 10. Okay, so we are trying to understand with this problem. Find the reverse current at 125 degrees Celsius easily. Okay, 125 degrees Celsius temperature. For silicon at room temperature he given how much, 50 nanoseconds. So that means what is the given data, is not he given, is not equal to what, is not equal to 50 nanoamps he given, 50 nanoamps, and delta t you need to find out, delta t equal to what, delta t equal to T2 minus T1, T2 minus T1, this is equal to 125 degrees Celsius minus 25 degrees Celsius. So this is what, 100 degrees Celsius, 100 degrees Celsius. So that means so I will find out the is. Okay, is equal to what, is not equal to 50 nanoamps. 50 nanoamps means what, 50 into 10 power, nano means how much, 10 power minus 9, no, nano means what, 10 power minus 9. Okay, 10 power 9 minus 9 and minus 9 into 2 power delta t is 100 by 10. So this one can get cancelled. So 50 nanoamps into this is 1024. 2 power 10 is what, 1024. So this becomes a nearer value, approximate value. Sorry. So approximate value if you take, this is how much, 51.2 microamps. Just this one you approximate to 1000. Okay, so 1000 means what, 51.2 microamps. So means previously what is the current in terms of nanoamps. Now if you increase the temperature to 125 degrees Celsius, the current increased to how much, microamps. The current is increased or not? See here, current becomes 51.2 microamps. Okay, so that means in the reverse saturation current, I can say that the current will double for every 10 degrees rise in temperature. I told you, no, current is due to minority carriers. Minority carrier currents are depends only on the temperature. Okay, is it fine? Shall I move forward? Yeah, give response.
Yes, sir.
Okay, so this is about the next yes, reverse bias. So here key points for PN junction with respect to temperature means German has high reverse current. Why? Because it is more sensitive to change in temperature. So I told you in the starting, germanium can withstand up to 100 degrees Celsius. It is more sensitive to temperature. Okay, and silicon and gallium arsenide has lower reverse current. Okay, it is less sensitive to change in temperature. So majority of PN junction diodes are made with what, silicon and gallium arsenide. Okay, we will not make the PN junction diode with germanium. Why? Because these are more sensitive to temperature. Okay, so we need to use our diodes in various climatical conditions. Suppose hot conditions above up till 150 degrees Celsius, or cold conditions minus 100 degrees Celsius or minus 150 degrees Celsius. Okay, so till this temperature these are stable. Silicon and germanium are stable, but these are not stable. Okay, this germanium is not stable, that's why we are not using for this one. Okay, so this is about the key points of PN junction diode. Okay, and next there is a capacitance are there. Two types of capacitance are there. One is depletion capacitance, and next one is depletion capacitance, diffusion capacitance. Okay, depletion capacitance and diffusion capacitance. So depletion capacitance or transition capacitance or space charge capacitance. So this is a capacitance available during the reverse bias condition. Okay, so reverse bias means you already seen. That means reverse bias means what? This one should be connected to which one? Negative terminal, and this one should be connected to positive terminal. Okay, so from this I can say that what is capacitance? Ct equal to, this is the basic formula, epsilon A by W. Epsilon A by W. So Ct is inversely proportional to what? W. It's inversely proportional to W. So what is W? What is W? We already seen W in reverse bias condition. So that is what? 2 epsilon by Q V naught plus V into Na plus Nd divided by Na Nd. That will add, no? So due to this electric field, so Q into V naught is nothing but this is the electric field under no bias condition. So this Q into V is nothing but what? Applying voltage. This applying voltage. Okay, so both are in the same direction. So electric field is from N to P, and electric field due to applied electric field, that is both are in same direction. This is E dash, we already discussed. So that means Q into V naught plus Q into V. So if you take Q common, you are getting V naught plus V. V naught plus V. So from this you can say that W is directly proportional to what? Square root of V naught plus V. V naught plus V. So what is Ct? Ct is inversely proportional to W, and this is inversely proportional to V naught plus V. Square root of V naught plus V. That means as V increases, W increases. As W increases, transition capacitance decreases. Understood? So here you have W equal to what? This formula. Okay. So from this, what is the relationship between depletion capacitance and width of the width? That is inversely proportional. As you increase V, the width increases. Okay, width increases. As width increases, capacitance decreases. Did you understood how I am doing this in reverse bias condition? Capacitance, depletion
Yes, sir.
capacitance and transition capacitance. Okay, so here you see that is depletion and transition capacitance, and diffusion capacitance. Diffusion capacitance is nothing but it depends on the mean lifetime of carrier. Mean lifetime of carrier. So mean lifetime of carrier means what? Suppose if you are applying forward bias, for forward bias what happens? Here negative ions are there, okay, and here positive ions are there. Here positive ions are there, okay, and along with this negative ions, what happens? Negative ions, and this is negative ions and positive ions. There are holes are there here, and here what are there? Electrons are there. Here electrons are there. So during no bias condition, what happens? This will recombine, no? So recombine, and that will disappear. Okay, so you are applying positive to P side and negative to N side, that we have seen in the forward bias. So what happens if you are applying positive to P side and negative to N side? Whatever the holes are there, that will be moved towards P side, N side. Whatever the poles are there, that will move towards N side, and whatever the electrons are there, that will move towards P side. So what happens? Hole is moving towards N side and electron is moving towards P side. These both will come and they will recombine and they will disappear. They will disappear. After recombination, what happens? They will disappear. Okay, after recombination. So after disappearing only, you are getting under no bias condition depletion layer, no, immobile charge carriers, negative ions and positive ions. Okay, so that means depletion capacitance is there in which bias? Forward bias. It is depending on which one? Mean lifetime of carrier. Till the carrier is available, till the electron and hole is available, then it is depending on mean lifetime. So what is CD? Tau by RD. Okay, tau by RD. What is RD? RD equal to eta Vt by Id. Eta Vt by Id. Okay, so eta Vt by Id, So that means CD equal to tau by RD, CD equal to tau by eta Vt divided by ID. So CD equal to tau ID by eta Vt. What is diode current equation? We already seen ID equal to what? I naught into e power V by eta Vt minus 1. Eta Vt minus 1. Okay.
Right.
So that means ID is directly proportional to what? E by eta Vt, no? E by eta Vt. So from here, CD is directly proportional to what? E power V by eta Vt. So as you increase the forward bias voltage, that diffusion capacitance increases. As you increase V, this value increases, exponential value increases. Why? Because this is positive value. This value increases. As this value increases, the CD also increases. Okay. So tau is nothing but mean lifetime, RD is the dynamic resistance, eta is the ideality factor. Okay. For germanium it is 1 and for silicon it is 2, and V is the applied voltage. Okay. So that means we can say that CD is directly proportional to E by E power V by eta Vt. So from here it is depending on this one. As V increases, the exponential part increases. As exponential part increases, CD also increases. CD also increases. Okay. So this is diffusion capacitance, and this is the capacitance with respect to applied voltage. See here. This is nothing but what? Transition capacitance. This is there in reverse bias, and this is diffusion capacitance. This is there in forward bias. Okay. So CD is what? CD is directly proportional to e power V by Vt. Okay. Vt eta you can take as 1, and CT. What is CT? CT is directly proportional to width of the depletion layer. Okay. So anyway, this is very small in reverse bias. Okay. The diffusion capacitance there is 0 only. Why? Because diffusion capacitance is there in forward bias. Okay. So CD is nearly 0 in reverse bias. Okay. And there is diffusion capacitance in forward bias. Okay. And here if you see, so transition capacitance is there in reverse bias. Okay. So that means as width increases, CD decreases. See here, as you increase more and more voltage, width increases. As width increases, CD decreases. Okay. Here in forward bias if you see, as width decreases, in forward bias width decreases, no? As width decreases, CT increases, transmission capacity. That's why it is increasing. Okay. It is increasing in the forward bias and it is decreasing in the reverse bias. Is it fine? Give response. Any doubt in this?